So a couple things to notice here. It says an object is moving along some curve in the xy plane. It gives you this position vector of x of t comma y of t. It doesn't really tell us anything about those. But it does tell us about dx dt and dy dt. So given that x of t and y of t are the position vector, what's the dx dt and the dy dt?
Velocity.
Those are the velocity components, right, of the velocity vector. And so understanding that, seeing that understanding those are the velocity components, then when you get to A and it says find the acceleration vector, you realize that to get to the answer for A, you need to differentiate each of those components one time, right? It'd be easy maybe to confuse those and think that they were something other than velocity components, but that's what they are. So did you guys use, for A, did you use Math 8?
No.
Oh, I should have.
You could.
I didn't think it was a calculator first.
Yeah, it definitely is calculator active. I think that'll come into play a little bit later for sure.
I mean, I wrote 12 cosine of 8.
So if you didn't, that's fine. D squared x over dt squared would equal cosine of t cubed times 3t squared. And then you evaluate that at 2. And when you evaluate that at 2, at t equals 2, what did you guys come up with for that? Cosine of 8 times 12. 12 cosine 8, I have no idea what that is.
Negative 1.746.
Negative 1.746.
Huh? 0.
There we go. Okay, so that would be the x component. Make sense? We all good there? Let me erase all that stuff because I'm going to run out of room. Okay, so we'll remember that negative 1.746. And then the y component, of course, would just be the derivative of the dy dt, the ddt of dy dt. So d squared y over dt squared equals negative sine of t squared times 2t. If you evaluate that again at t equals 2, similar type of a situation here. What number do you guys come up with for that one?
3.0272.
Okay.
Can't read that.
I struggle with that sometimes too. Okay, so that would be your acceleration vector when t equals 2. That's it. A. Any questions on A? Okay. So for B says write the equation of the tangent line to the curve. So when it says the curve, remember what we're presupposing here is that this object moving around is basically laying down a path, right? So it's leaving like a highlighted path that it is moving along. And so we're going to pick this point where t equals 2, and we're going to say, all right, this is whatever point on the curve this is, that's our point of tangency, and we're going to try to determine the equation of the tangent line at that point. So this object might be moving around like this, and we say, all right, well, right there when t equals 2, we want to know what the equation of that tangent line would look like, something like that, and we're going to use the information that we have in order to try to figure that out. So we have a lot of the information that we already have it. And so let's think here. If we're going to find the equation of the tangent line, we need to have those two big things. What are those two big things?
The slope of the line at the point.
Yep.
And the point.
Yep, slope of that tangent line and the point of tangency. And we already have the point, right? They just gave it to us. Where is it? 1, 4, right? So they say when t equals 2, the object is at position 1, 4. So if I wanted to start kind of building out my point slope form, I could write y minus the y coordinate is equal to blank times x minus the x coordinate. I've got to figure out what the slope is. But I've got that part, right? That's nicely set up. And then as far as the slope, when you are given vectors in this parametric form, slope of the tangent line, regardless of whether you have x's, y's, t's, r's, or thetas, or whatever, slope of the tangent line is always what? dy dx. And so with this situation, both y and x are in terms of t. And so what would be that basic format for dy dx in this situation? There it is. Yeah, it's the same as the parametric we learned in December. So dy dt over dx dt. And of course, the good news is, don't we already have dy dt when t equals 2? And don't we already have dx dt when t equals 2? Weren't those the components of the vector we found in A? We've already got them. So why bother doing anything extra? Here's your slope. Well, if you want to, that's fine. So it would be dy dt at t equals 2 would be 3.027 divided by negative 1.746. That would be, whatever that number works out to be, would be the slope of your tangent line. And I think we got it, right? It's in point slope form. It didn't specify which form. Caleb, you kind of have the frown going on, the question frown.
Didn't we get the acceleration in part of it?
Oh, we did acceleration. Darn it. I wasn't thinking. Sorry. That's I can't blame that on Monday morning or anything. Let's get rid of that real quick before somebody sees it. So, but we already do have what we need, right? We don't have to do any extra work. We're just going to use, goodness gracious, this is all we need right here. We're just going to use those two. Hey, don't make Caleb do the I have a question frown and make me like interpret that. Just say if you feel like I did something wrong, just ask. It's okay. So we can make this similarly easy though. Couldn't we just say cosine of 4 over sine of 8? dy dt at 2 over dx dt at 2? Okay. Again, I don't know what that decimal, if you did that approximation, work out to be.
Negative 0.6607.
All right. Negative, you said 0.
Yep.
0.0667?
No. 0.6607.
6607, negative. Okay, fair enough. Okay. Part C, find the speed of the object at t equals 2. This is, I mean, depending if you're a physics person or a calculus person or some blend of both, you could think of this as being very formulaic. You could think of it as like a resultant vector if you're a physics person. The formula, of course, is square root of dx dt squared plus dy dt squared. This is your formula for the magnitude of the velocity vector, also known as speed. We want to know what's going on when t equals 2, and so we could then take this and just apply it specifically to our situation. So it'd be square root of, let's see here, so dx dt at 2 would just be sine of 8, so it'd be sine of 8, quantity squared, plus cosine of 4, oops, there we go, quantity squared. That would be a good representation. If you wanted to use the calculator, you could take it that one extra step further and get a decimal value of, anybody do it?
1.1858.
Whoops. 1.1858? Okay. 858. Okay. And then the last component of this here is D, find the position of the particle when t equals 1. And so, of course, we were told that the position vector is x of t comma y of t, but we were not given the position vector. If we had been, this would be a really, really easy. Plug it in and you're done 2 seconds later. We were given, of course, information directly about velocity. And we really do have to use a definite integral here because the indefinite integral for those two components of velocity not going to go so well. And so we are going to use definite integrals. So for the x component, you could do something like this. The original x position was 1 plus a change. So it would be plus the integral from, let's see here. Interesting. Oh, I'm sorry. I was going to talk to you guys about the ordering of the times. We can do that in a second. Your question, McKenna.
Well, I just didn't get how you know if it's like 1 plus or 1 minus.
Well, so that's what we're going to kind of talk about here. We could approach this in a couple different ways. And so maybe I can address your question and maybe address the other side of that right here. So let's do this. If you just want to do a generic definite integral, then what I would say, you could just set it up as, and this I think would clear it up for you. You could say the integral from 1 to 2, because we're used to accumulating from left to right. And I'm picking the 1 and 2 because we're interested in this, and I know this. So integral from 1 to 2 of v of t in the x direction. So that would be sine of t cubed is equal to, I would say this is equal to x of 2 minus x of 1. And the reason why I feel comfortable saying that is because I've got the ordering the way that I want it, right? So I'm integrating from 1 to 2, and using FTC 1 and 2, it would just be the high, like the physically higher value minus the physically lower value with FTC 1. So based on that, I know that x of 2 is 1, right? And so I would say this equals 1 minus x of 1. Does that make sense? And then we need to use math 9 for the left side. I don't know what that is. Do you guys? Did you guys parse that out, or did you just do the arithmetic?
No, 0.21 equals.
Yeah, it's
So yeah, so then you're gonna subtract the 1. Is that just is that math 9?
math 9 of the integral from 1 to 2 is 0.218. So then I like
0.218.
subtracted that from the other side and added the x of 1.
Yeah,
That's
that's what I did.
what I did.
Okay, so
To get rid of the negatives.
so yeah, so if you subtract, so you're gonna get like negative 0.7819. Okay, and positive number, right? 0.7819 equals x of 1. So what I'm doing there, of course, is subtracting the 1, dividing by negative 1. Make sense? Okay. And so McKenna, does that clear up your question too? Like, do I add or subtract? I think this might be the case where instead of looking at it as original plus change, maybe it's easier just to think of it as FTC 1 and 2. Okay, you bet. Okay, and then the other one will be really similar to that. It would be, for the y's, it'd be integral from 1 to 2 of cosine of t squared dt. This will equal y of 2 minus y of 1. And I know that y of 1 is 4. No, I know that y of 2 is 4. So y of 2 is 4 minus y of 1. And again, obviously you got to use math 9 for that left side. Anybody have that?
Negative 0.443.
Negative 0.443. So then you subtract 4. So it looks like we're going to get positive 4.443, right? 4.443 equals y of 1. Okay, so then what is the position of the particle? You could answer that question just by putting those two together and saying the position is 0.7819. Comma 4.443. Okay, so yeah, be careful with the ordering there, and of course the plus, the minus, and all that stuff like you asked about. Hope that clears it up. How'd we do? Any questions? The one thing that this question didn't really cover that we have covered 2-3 times already is that concept of total distance traveled, right? It's the same as the parametric length of the, length of the curve or arc length. So be aware that that's one thing we didn't cover here.
Are we going to need to know the angle of the particle at all? Because we haven't done any problems that involve that formula.
Sure. Well, so tangent of the angle equals dy dx, right?
Right.
And so we could do that right here. So if you had an additional question, let's say on this one that said, what is the angle of the particle when t equals 2?
Okay.
Or something like that, then you would say, so I'll try to squeeze this in right over here. So let's say it said, what is the angle of the particle when t equals 2? You would, start off with that formula, tangent of theta is equal to dy dx. Well, we know what dy dx is, right? We have that from right here. So that would be cosine of 4 over sine of 8. So you'd say tangent of theta equals cosine of 4 over sine of 8. And then to get the angle would be theta, right? So, and this would definitely be a calculator active question, because then it would say, all right, well, hey, if tangent of theta equals that, I would just do the inverse tangent of both sides. So theta equals inverse tangent of whatever that, I guess Blake gave us that decimal earlier, at negative 0.6667 apparently. And yeah, run the calculator on that. So that one tends to be like kind of a plug and chug sort of a thing, right? Because you're gonna, dy dx is gonna be something you'd build from, and this is a pretty rare one as far as being asked. I know it's been asked very occasionally, like in an AP setting. So that's why I'm not making it like a really big point of emphasis. I feel like speed, total distance traveled, but it has been asked, and so that's why it's not.
Okay.
So yeah, thanks for asking. Anybody else? Lenny?
So why wouldn't you use the position at like 1-4? Because wouldn't that just kind of show the coordinates and then you can use like a right triangle?
Use the position at 1-4.
Yeah, because it tells you the position, then maybe you just do tangent, like the inverse tangent, and you have the x.
So you're talking about the angle from
Like origin, I guess?
the origin?
Like what angle do we?
It says the angle.
Angle from what?
So let's see here. We could draw a picture of that. So where am I going to draw a picture of that? I don't know. We'll find out. So what might be helpful for you? Grab your calculators. Why don't you all graph? Hang on. Let's see here. Hang on. What would I want you to graph? Let me think here. I'm thinking. Way to get to the same types of places that we got to using rectangular coordinate system. So, for example, this would be weird, but if I was standing here and I wanted to go talk to Darian, couldn't I get there in really a couple different ways? Couldn't I turn straight south and walk 9 feet, get to about here, then turn straight west, and then walk 3-4 feet this way? And then I'd get right here by Darian, right? What system am I using there? Rectangular coordinate system, X's and Y's, right? Or, the way that we normally do things, we actually typically walk, when we're moving around, we typically move in a more of a polar type of a philosophy, right? I'm never going to, that would be weird, wouldn't it? If I just like, okay, I'm going to go see Darian and I do that. You'd be like, why are you walking that way? Wouldn't it be smarter for me to turn at the appropriate angle and walk straight ahead? That's more of a polar way of thinking, right? So with rectangular coordinates, you have X's and Y's. You have to operate on a grid, just like you have to do on city streets. And wouldn't it be awesome if to get home, all you had to do was point your car in the direction of your house and drive straight ahead? It'd almost be like being in an airplane or a helicopter, wouldn't it? That's why, of course, those are so efficient, other than being faster than cars. But when we're walking around, we typically operate in a polar fashion, right? It's mentioned down here at the bottom, I'll do this now, but there's no one way to get, there's no one exclusive way to get somewhere using polar coordinates. So one of the ways I could get to talk to Darian is I could point this direction and walk straight ahead, right? Aren't there other ways I could use polar? Couldn't I point in the exact opposite direction and walk backwards? I'm still here. I'm going to have to kind of like talk over my shoulder to him, but I'm still in the same spot, right? Well, not only could I do that, I could do this and then walk backwards, right? Or if I was really wanting to make myself dizzy, I could spin around a bunch of times for whatever reason and then walk straight ahead. Sideways, no. You have to walk in the direction you're pointed or the opposite direction. But yeah, no sideways. Yeah, so polar is kind of unique, right? It's different. To get to a point, a rectangular coordinate system, there's like one unique representation. Like 2, 5, there's only one way to get there in the rectangular coordinates. You go 2 to the right and 5 up. But to use polar coordinates to get somewhere, there's actually an infinite number of ways you can get there. You'll discover, if you do take a Calc 3 class, that there are other coordinate systems. There are spherical coordinate systems. There are cylindrical coordinate systems, different ways to get to all these same kind of places. Those are for 3 space or 3 dimensions. We're still living in 2-dimensional world here. But just so you know, there are other ways that you can get to different places above the plane too. So just be aware of that. Theta in this scenario, theta is the angle that you turn to. And I'll put this, it's the angle from the positive x-axis. A lot of people have a kind of a misunderstanding of polar. They think, well, polar and rectangular, they can't be together, they can't function together, but they can. And as a matter of fact, on my little picture here, this is the x-axis. And this is the y-axis. It's not like the r-axis and the theta axis. That's not what it is. It's still the x and the y-axis. We're just going to use theta, an angle, to get pointed in the right direction. And then r is the distance from the origin. And then with polar coordinates, we sometimes refer to the origin as the pole. It's the thing that you rotate around. So an example here, graphing 2 comma 4 pi over 3. What we typically do, what I typically think of here is I try to turn to the angle, turn to the appropriate direction first, and then I'll move the 2 spaces, the two units in the right direction. So 4 pi over 3, so let's think about how this would work. I'm facing this direction. That's going to be theta equals 0, right? That's kind of our baseline direction. And I'm going to turn 4 pi over 3. And just like we've always done, we are going to turn the counterclockwise. So I'm going to turn to 4 pi over 3. So let's see, that's a little bit more than pi. So if I were to turn this far, I'd only be at pi over 2, wouldn't I? If I keep going over here, I'd be at pi. And then a little further, something like that, would be at pi over 3. 4 pi over 3, excuse me. And so this big dot that I'm putting here, this big blue dot, that would be my location for 2 comma 4 pi over 3. I turned to the appropriate angle and then I moved forward 2. Like I said, there's other ways this could happen. Let me give you maybe one more example of a polar coordinate that could show up. So there's that one right there. I'll leave that in blue. That's 2 comma 4 pi over 3. You could have a bunch of negatives. Like you could have negative 3 comma negative pi over 6. Polar coordinates, right? So negative pi over 6 for an angle means we're actually going to turn clockwise. So we would start off facing 0, and I'm going to turn negative pi over 6. So that's not very big of an angle. It's right about there. So at this point, from the origin, I'm actually pointed in that direction, right? That's the direction I'm facing. If you think of yourself standing on the origin, spinning around, you're pointed in the direction of the dotted line, right? From the origin. But because the radius is negative, aren't you going to walk backwards? Like I did in that example with Darian. So I'm going to actually be moving this away. And I'm going to end up right about there. So I'm pointing negative pi over 6. So I'm pointing this way. But because the radius is negative, I'm going to like walk backwards. I'm going to go opposite the direction that I'm pointing. Does that make sense? Mm-hmm. And you could have combinations. You could have a positive angle and a negative radius, or a positive radius and a negative angle, and all the other different combinations of spinning multiple times, which we won't do because what's the point? We reserve that for the trigonometry part of pre-calc, right? When you got to spin around like 20 times, then finally find your reference angle. It's like, yeah, okay, whatever. Anyways, so you end up right here. This would be that second point. So from a really basic perspective, are you guys understanding like a polar coordinate? Yeah. Make sense? because this will be the foundation for all these other graphs. Okay, so I mentioned there's infinitely many ways to get to a spot using polar coordinates. Of course, because the x and y axis are still active here, we can convert between polar and rectangular. And hopefully this looks pretty familiar with what we've been doing. And then also, if you've had physics, you understand how these conversions work with components and such. These are all useful, helpful, happy things. Especially these two will be used a lot when we get into the calculus of it all. X equals r cosine theta, y equals r sine theta. So file those ones away. Those will be used a lot. This should look familiar, right? This is actually kind of what we finished with from Darian's question a few minutes ago. And then this, of course, is the Pythagorean theorem. So all four of these things really are things that you've learned in old classes, past concepts, and they're just kind of resurfacing here when it comes to polar. Keep in mind one thing. I want you to get kind of the big picture here. I mentioned earlier, polar coordinates are simply a different version of parametric, right? Parametric simply means that there is a parameter that's influencing the x's and the y's. So up to this point, the parameter for x and y has always been t. Now, if you look at this, you realize that the parameters for x and y are now r and theta. Now there's two parameters for x and y. Keep that in mind. Again, from a Calc 3 perspective, if you end up taking that in the future, parametric ways of expressing things is very, very common. And this is just a different version of parametric. Okay, let's take a look at a few graphs here before we wrap this up for today. Yeah, polar graphs. Beautiful. We'll try to get through several of these. If at any point, I want to make sure this is really open to you guys. As we investigate these, we'll do a mix of kind of doing this by hand and doing this with a calculator. If at any point you want to kind of fiddle around with the calculator a little bit, all you have to do is put it in polar mode. If you just go to mode, there's rectangular, parametric, which you've used. There's polar mode, which comes next. And there's sequence mode, which we'll use next chapter. Yeah, but you could go to polar mode. You can play around with these yourself. In fact, I would encourage you to do that and come up with all kinds of cool things. Okay, so the first one is just r equals 2. And if you think about it, all this is really saying is that the radius is 2, and it gives us no direction about the angle, does it? So that means the angle could be whatever you want. Big, small, negative, positive. The angle could be anything you want, but the radius must be 2. What is this really describing?
Circle.
A circle. Yeah, all it is a circle. So the radius has to be 2. I was going to be cutesy and make my circle. It's kind of tough. Hey, there we go. Got it. Okay, so that would just be a circle, radius 2. Angle can be whatever you want. Obviously, the origin for all of these is going to be kind of that central point of rotation. So all it is just a circle. Okay, the next one, theta equals pi over 3. This is the exact opposite line of thinking. This is basically saying that the radius, the distance from the origin, could be anything. There's no restriction on that, but the angle must be pi over 3. So if the distance from the origin is whatever you want it to be, it could be anything, the angle is that. What is this describing? It's a line. Yeah, it's a line at an angle of pi over 3. So that could look, let's see here, pi over 3. That's a little too steep. We'll go with that. Pi over 3. Just a line. Does that look about the right angle? I'll put arrows on the end because it can keep going. Okay, and then r equals secant of theta. So this one on the right here, of course, is the first one where r and theta are both in play, right? R depends on theta. So this is also kind of a unique one. I don't know, anybody do this on the calculator yet?
Looks like a line.
Should be a vertical line.
Yeah.
Should be a vertical line. So let's see here. I'm debating about how much I want to do with this. You can plot points. You can plot points here. So for instance, like if you said when theta is 0, what's secant of theta?
DNA. Wouldn't it be like 1 over cosine?
We 1 over cosine, and cosine of 0 is 1, yeah. And of course the reciprocal of 1 is 1. So I would say when we're pointed straight to the right, then the radius is 1. Oops. Come on. Why are you giving me trouble? You just are. There we go. Okay, so there's that point right there. And if you plotted points, this of course gets kind of laborious. Like if you say plotted pi over 6, pi over 3, pi over 4, and you did your best to approximate those, you're going to get a bunch of decimals, of course. What you're going to find is as those points get plotted, like there would be pi over 4, here's pi over 6, pi over 3 would be up here somewhere. You do some negative angles, you'd find this nice vertical line forming. And really, to be honest with you, as we explore these, I think one of the best ways for you to kind of understand what's happening in most cases is really honestly to plot points.
Can you just like multiply cosine on both sides?
Yeah, you can. I was thinking about a conversion. We can do that if you want. But my point is simply that sometimes, just like plotting out the points and saying, all right, what exactly does happen here, sometimes is your best bet. So anyways, yes, you can do it. I only had like 1 minute left, so I'm like, what do I want to do? I decided to plot points, but you can do a conversion as well. So when you guys come to class tomorrow, we will just continue exploring and messing around with these. Please have your calculators. We'll use those a lot. Otherwise, I think we're good. Have a wonderful rest of your day. McKenna, what's up?